William Irvine from Chicago, who is just here for a day, but we hope he'll be back in December for a more extended period. He was one of the coordinators of the recent program in Santa Barbara. Some of you were there, I think, on knotted fields. And so I was in touch with him over that and jumped at the opportunity to have him come and give a seminar when I knew he was going to be here, even for such a short visit. So, William, this is Knots in Physical Fields. Over to you.
Thank you. I should begin by thanking Keith for the invitation. It's a real pleasure to come out here and talk to you. This is in fact the place where a lot of what I'm going to talk about started. And in fact, I realized last night that most of the references in my talk and in the paper that we're writing are in fact in the audience. So I look forward to some interaction. And I should start by saying, please feel free to interrupt at any time, and it's nice if it's a dialogue. So what I'd like to tell you about today are two problems. The first one, which I've sort of represented over here with this kind of cartoon, is a problem in which we wanted to look at solutions of Maxwell's equations in free space. And we were interested in looking at solutions where the field lines were knotted and linked or had non-trivial topological structure in some way. And this is, at the moment, entirely theoretical work, although it could be transferred to experiment without too much difficulty. And on the right, the second topic is experiment. And I want to tell you about experiments in which we tried to create vortex loops, but not trivial vortex loops, the unknots, which we're all familiar with, but vortex loops which are tied into knots and linked to each other, and study their topological evolution. And of course, they're sort of different systems, and one's experiment, one's mostly theoretical, but what they have in common, of course, is a strong role played by the topology, the global topology of the structure. That this talk here is not about tying pieces of rope into knots. It's about tying entire fields into knots. And when you want to tie a field, like an electromagnetic field or a flow field, you have to worry, of course, not only about the knot at the core, but how you fill the rest of space in. And it's, of course, hard to talk about this without paying homage to sort of where it began, around the corner, I think, with Lord Kelvin. And the story goes, at least as I was told it, and please correct me if I'm getting my history wrong, that he was attending a lecture on circulation theorems, Helmholtz circulation theorems. And part of this lecture was a demonstration by Tate, Peter Guthrie Tate. And the demonstration might have looked something like this. The person you see over here is actually Dustin Kleckner. He's a postdoc in my group who's responsible for a lot of the work you're going to see in the second part of the talk. So it's quite cool, exactly. It's striking. And this was, of course, the time when nobody really knew what atoms were, the ether was still in fashion, and the lectures were on the stability of these objects. In a perfect fluid, if you make a vortex loop like that, you can never break it apart. And so at least the story goes that he had the intuition.
Came a couple of years after
It was a couple.
Kelvin saw this experiment, yeah.
Oh, okay. So it wasn't a lecture on the circulation theorems.
It stimulated him to.
Okay.
So the Cardassian
There you
fluid
go.
just pushes a membrane, or it's more complicated?
No, you just push a membrane.
Okay.
You can in fact buy these on the internet, at least versions where you have a little trigger even that you sort of okay.
Can you blow a trafile knotted smoker?
Second That's coming.
Wait a minute.
People have tried. Okay, so the story goes that then of course that was the idea that was planted, and that led Tate, who was fascinated by this, to start to classify and tabulate knots, presumably in an effort to find a mapping onto the periodic table. And as we all know, that sort of failed, of course. That atoms are not thought to be knots in the ether, which permeates everything. But nonetheless, the seed was planted. In fact, more than one seed was planted. The first seed was the Tate table. Now there was a table which classified knots, and somebody had to do something about that. And so knot mathematics was sort of born of understanding and classifying it. And the other one is the notion of topological states and non-trivial topologies in physically realizable fields. And this has sort of since come back over the years in various guises and forms, in fluid dynamics, as we'll see, in plasma physics. It's sort of also in relatively exotic field theories, in gauge theories, and contexts like that. But there's been a sort of recent resurgence, which I'd like to point out, driven by the fact that one can access these topologically non-trivial states in physically realizable systems, and not very, very impossible to measure systems or very challenging systems, but more down-to-earth systems. And it's sort of driving a renewed interest in the field. And just to give you a few examples, there's a few over here. This is work which I'm going to talk about in the first part of my talk, in which we looked at knotted structures in free space. There was some recent work by Mark Dennis and collaborators where they looked at vortices, like the ones which we're going to see in the second part, but in light fields. And they succeeded in tying them into knots, both in theory and experiment. There's some experiments recently on liquid crystals, where you take liquid crystal states and you make them with non-trivial topologies, both in a sort of, let's say, space-filling form, and you, in the case in which you concentrate the knot on a defect line in the liquid crystal, and then you fill the rest out from that, which was work in Sumer's group. So all these different systems, and there's of course fluid dynamics and plasma physics, which I'm going to come back to later in the talk. And in all these systems, you're sort of tying, if you think about this as how do you tie a knot in a field type problem, in all these systems you have different objects which you're tying, but a common set of problems. Okay? You have an initial state design, which is non-trivial. You have to come up with this configuration in the first place. And you then have physical constraints, which come from the physics of the system which you're tying the knot in. And all these come into play with each other, with the design. And what I'm going to try and do is sort of take the point of view of, I called it the topological designer tongue-in-cheek, but just try and take that as a narrative for the work which I'm going to show you. And of course, the hat over here was a homage to Ken Millet, from who I learned a lot of the basics of knot theory. This used to be a hobby of mine, a sort of nighttime hobby when I was a graduate student. And what little I know of knot theory, I learned from him. And I always remember Ken by his, well, I remember Ken as Ken, but one of the sort of defining characteristics of Ken outdoors is his hat, which I learned recently, unfortunately, is no more. But nonetheless. Anyway. When I gave this talk at the KTP, you showed up with a baseball cap, and now, so I'll have to make an interchangeable slide. Anyway, so let's get down to business. The first part I'm going to tell you about is knots in light fields. So the degree of freedom which we're going to be tying, which we're going to be considering, are magnetic field lines or electric field lines. I'm not going to be considering any connection between the two, either one or the other. And most of us sort of come across magnetic field lines in a high school experiment like this. You have some iron filings, a magnet, and they organize themselves to form nice field lines which are tangent everywhere to the field. And this is a sort of nice demonstration. It's a picture you use to describe them. They also pop up in a lot of sort of magnetic field lines in magnetohydrodynamics, in contexts in which you're trying to understand complex flows of charged particles. Here's a picture of some field lines coming in and out of the sun, lit up by charged particles which are going around them. But of course, when it comes to light, you usually don't work with field lines. You work with field lines in these sort of situations, where they're conserved and they're essential to the physics. Light you usually described by a plane wave. It's a simpler parametrization. You'd think of light as a bunch of plane waves. They have a wavelength, k vector, and in fact their field line structure is completely trivial, so you don't normally consider it. So what I want to do is sort of depart from that, and purely out of intellectual curiosity, I want to consider states of light whose defining and most interesting property is the structure of their field lines. And if you want, you can think of this as a form of linearization of the problem. I want to consider topological structures in a linear theory and see what we can get in that case, just to keep it as something to bear in mind when we consider nonlinear theories. And you want to differentiate what structure comes from the nonlinearity and what structure comes from linearity. And of course, what I mean by topologically non-trivial in this context over here is going to be, I'm going to consider field structures which have non-zero linking number. Okay? Now, of course, everybody here is familiar with the linking number, but if there's anybody who isn't, let me sort of walk us through it. Linking number is a number you can ascribe to any pair of closed curves. It's very simple to compute. You can compute it visually. You just take the two curves and you essentially drop them on the floor, and you give them an orientation before you do that. You have that for free if it's a field. And you go and look at the crossings. And at every crossings, you have a cross product from the two directions, which gives each crossing a sign. And if you add all the signs of the crossings, and divide by 2, you get the linking number. Okay? And the important thing, of course, is that this number does not change under any ambient isotopy. It's a topological invariant of the structure. But of course, what we're interested in is fields, not curves and lines. So we need a measure which involves the field as a whole. And this is where Keith comes into the picture. The quantity which measures the linking number, or the linkedness and knottedness of a field, is the helicity. Shown here is the magnetic helicity. It always comes in this form over here. You have here A dot curl A. B is just the curl of A. And that's a measure of the knottedness in B. Okay? And it's not obvious if you look at this expression. You sort of have to work a little bit to see that this is the right measure. But you can do that by breaking the field down into tubes, into flux tubes. And then you can ask, well, what if I compute the, let's say, the average or the sum of the linking number of all these flux tubes that contain field lines weighted by the flux? And then you can make this continuous by considering an infinite set of tubes and taking the limit as the number of tubes goes to infinity, the flux of each tube goes to 0.
Is A the vector potential?
A is the vector potential in this particular case.
It says nothing about electric field.
No, but in free space there's duality, so it's exactly the same statement. You have an analogous field, you can call it C, such that E is equal to curl C, and the whole structure carries across independently. So this is about breaking up electric and magnetic, but you can in fact do the same things with each other. Now, of course, you don't want to go and calculate this linking number for each pair visually. Okay, you want to use something so that you can get back to this expression, and the expression you use is the Gauss linking integral. Okay, and without sort of trying to rederive it or put it in context, especially with this audience, for those unfamiliar with it, you can just convince yourself that it's at least related to the visual computation we did before. You have a combination of 3 vectors over here, the tangent to one curve, the tangent to the second curve, and you have the line joining the 2 curves. And if these are in a plane, this is always going to be 0, except at the crossings where they have to come out of plane. So this integral is a way of counting crossings. Okay. But you can also sort of derive it many ways as a degree of a map, and et cetera, et cetera. But then essentially, once you have that expression, you can sort of commute between the two easily, and you can see helicity as a measure of the knottedness. So this is in fact our first kind of design consideration. We're going to consider fields where the magnetic field lines have non-zero helicity. And so, in fact, the context in which this was introduced was in fluid dynamics, where it was already known that helicity was a conserved quantity, and also in MHD, helicity was known as a conserved quantity before the topological interpretation. But in free space, you have to ask, in free space there's nothing that breaks field lines. So what would conserve this topological measure of the structure of the field? And the way you do that is by just taking the time derivative of it and simplifying it using Maxwell's equations, and you find the following condition. So this helicity, the knottedness of the magnetic field, is conserved on average as long as the integral of E dot B is 0. So from the point of view of designing fields, this is your first design constraint. You want fields such that the integral of E dot B is 0. And you immediately see that we're interested only in B, but because of the dynamics, because of the physics of the field you're tying, immediately this auxiliary field, the electric field in this case, comes into the picture. Now, we could try and construct all sorts of fields configurations with, say, average knottedness, which is positive somewhere and negative somewhere else, and averages out. But wouldn't it be nice if you could make a field where all the field lines have the same structure? So the first thing I want to do is convince you that such a configuration is possible.
The time is, what is the time of the previous thing? So you have some relaxation process in the background, or it's
Yes.
the time, there's a process
The process is evolution of Maxwell's equations.
by Maxwell.
By Maxwell's equations, yes. So the only ingredient you put in is Maxwell's equations. So there's a structure which many of you might be familiar with, known as the Hopf vibration, and it can be seen as a way to fill space with loops, with circles, such that any 2 circles are linked with each other. Okay, so we'll just construct that briefly because it'll play a big role in what I'm going to tell you soon. And you can build it by starting with a torus. Okay, so you take a torus and you draw a line that goes once around this circumference and once around the other circumference of the torus. And if you do that, you get a line that looks just as in the figure. That's just a plot of this. Okay, there we have a line. And then what you see is that if you like, you can in fact go ahead and draw another line with the same structure. Okay? The same rule. You just go once around each circumference. And these two lines don't cross with each other. They can smoothly fit on the surface. And then if you, and this is the bit where I get a little nervous, hopefully I did this right. If you remove the torus, you see that the two lines are linked to each other. And the nice thing is that there's no obstruction. You can keep doing this. You can keep adding lines to your construction, and you can form a torus such that any two lines are linked on the surface of the torus. And then you can nest the tori inside each other. Yeah, a little bit like Russian dolls. And you'll see that each one of these is made up of lines that are linked to each other. And everybody which is lying on the, let's say, the outer torus goes at least once around this circumference. Anybody on the inner goes at least once around this circumference. So everybody is linked to everybody else in the field. And then we can remove our constructing tori and just think of breaking up space in this manner. And there are two, sort of this structure is sort of very complex, but on the other hand, it's very simple. You can summarize it with just two lines. You have a line that goes on the infinitely big torus, from minus infinity to infinity, and a circle. And you can sort of fill the rest out by eye, just given those two lines. The only extra ingredient you need is to know whether it twists one way or the other way. So we're going to be representing the structure just with these two lines plus one of these tori to give you the sense of the twist. Huh?
You've chosen the 1-1 wrapping.
I've chosen the 1-1 wrapping, yes. And we'll come back to the 3-2 wrapping. It's quite different, the 3-2 from the 1-1. It's subtle. Okay. But of course we want to do electromagnetism. We don't want to just draw pictures, so we're going to need a formula for this. And the nice thing again is that this whole structure can be represented with a very simple complex scalar field. And the only thing to take away, apart from the simplicity of the expression, is that the lines, the circles which I've been drawing, are lines of constant amplitude and phase of this map. And the tori are the sort of lines of constant amplitude of this map. And in fact, this already introduces another step which you can come into design. You can study all sorts of maps. In fact, it sort of starts as a map from S3 to C, and there's various classifications of these. And you can sort of start studying ways of using different types of maps to design fields. But I want to concentrate on the simplest one, the 1-1 case, because I think this will actually be a useful journey which then comes back and tells us what the rules are for designing. And so rather than go through a derivation, it turns out that the 1-1 case has in fact been considered before. Okay, and I had the recycling sign there just as a sort of informal joke. How long has to pass between rediscoveries for them to be considered rediscoveries? But of course I mean that only tongue-in-cheek. What's really going on is these solutions were considered first by Bateman in 1910, more recently by Robertson and Troutman, and Ivo Bianchi-Birula and Ragnada and myself and collaborators. But of course what actually happens is at each stage somebody stumbles across this solution for completely different reasons. And Bateman was interested in potentials for null solutions of Maxwell's equations. Robertson and Troutman were interested in the relativistic structure of solutions to Maxwell's equations and how you could use that to tell you about the structure of space-time. And Ragnada was interested in sort of a more topological formulation of electrodynamics, although some of the constructions which led to this don't seem to generalize so easily. And my interest was really to sort of take this from a point of view of I want to make all sorts of solutions and what are the rules for knotted fields rather than this one special solution. But by studying this one, we can get to that. Okay. So the result of, you can pick your favorite construction, but the result is something like this. You get an electric field or a magnetic field completely equivalently. The two have the same structure, which is given by something like this. It's a gradient of this function cross the gradient of the conjugate. So it's going to point along lines of constant amplitude and phase. The tangent curves of this field are going to be these circles, which we considered. You can make it HG, you can make it HZ. It's just a question of orientation. There's a 3Gs. Okay. And so what I want to do is just take that and solve for the time evolution. Or at least I'll take it that you trust me that I can solve for the time evolution. And I just want to look at what this solution does. We're going to look at the physical properties and the evolution. And so what I'm showing you over here are the electric field lines at time 0. It's one of these Hopf vibrations oriented along x. These are the magnetic field lines at time 0. It's one of these Hopf vibrations oriented along y. And we're going to look at their evolution. So that's the evolution of the electric field lines of this solution. And what you can see from it is that the field line structure, the topology of the solution, is preserved very, very smoothly. There's a bit of a deformation, there's a twist, and a little bit of a propagation. Okay. The magnetic field lines do exactly the same, except they're, in fact, rotated by 90 degrees.
It's expanding at the speed of light, is it?
It's expanding at the speed of light, yes. And in fact, you can summarize the whole evolution. It looks a little complicated, but actually, if you go back to thinking just about these two lines and you look from above, you can see that the whole evolution, you've in fact witnessed the whole complication of the evolution. Okay, there's just a twist and a propagation forward and a rotation. Okay? And after here, it just sort of slowly asymptotes. Okay? So you've seen the thick of it, as it were.
So if you scale back, you don't get a periodic behavior. There's an asymptotic behavior. It's just like a single twist.
Yes, exactly. It's, in fact, there's no oscillation. The spectrum is broad enough. We'll come back to that. But there's no oscillation in this field. So that was the field line structure. But where's the energy? Where's, if you want to look at this in physical terms, you want to know where the energy is. This is what the energy density looks like at time 0. It's just a sphere. I just plotted E squared plus B squared. Drops off as 1 over R38 as you go far away. And if I turn time on, I'm just plotting over here a level set and 3 cuts through the energy density. And if I turn time on, you see that it evolves in the same direction. So the energy density coincides with the field line structure, and it evolves preferentially in one direction. It looks a little bit like a beam of light. And in fact, I can dial time back, and then let it come forward, and it looks very much like a beam that's coming down, being focused and expanding. And here is a sort of plot of all 3 structures together. We have the energy density on the background and the electric and magnetic field lines together. So you can sort of look at this. You can also, of course, calculate all the charges that this solution carries, the properties, and you see that it has, well, of course, it has energy, it has momentum, propagates mainly along z. It also carries angular momentum that turns out to encode this twist, and there's various other conserved quantities that one can associate with it. But what I want to do now is I want to take it apart. I want to take the perspective of, imagine you wanted to make, so now you've seen it's like a beam of light, so imagine you want to make it. You want to make it down into building blocks that you might be familiar with in the lab, and we'll see what this tells us about the solution itself. So what I want to consider now is what happens if you take this solution and you decompose it into a basis. And it turns out, this actually took me a long time to realize, that the most natural basis for the solution are the vector spherical harmonics. Okay? So these are just the kind of eigenstates, if you want, of associated with the rotation group. They carry a few labels, 2 polarizations because it's vector, and then they carry the usual L and M, which are the angular momentum components. Okay? And in general, you have some horrendous decomposition of the field. But if you decompose this solution into vector spherical harmonics, you see that in fact it has a very, very simple structure. Okay? You lose the summation over all possible angular momenta. It's a pure angular momentum state. L is 1, M is 1, so that's only information I need to give you about the rotation properties. Both polarizations come in with the simplest phase factor you could imagine. It's I, so you've sort of broken that, you've reunited them, if you want, into one object, TE plus ITM. And the energy spectrum is also very simple. So now all I need to tell you are these 3 things, and you can reconstruct this solution, and you can sort of think about its physical properties. And this is interesting, because in the lab, if you wanted to try and make one of these, you'd start with trying to make the single frequency vector spherical harmonics. But you can also ask, what does it tell me about the solution? And so what I want to do is sort of pull this expression apart so we can put it back together. And the first thing which I noticed is that if you take this object over here, this TE plus ITM appears. There's no degeneracy. The degeneracy between the two is maintained. It's not broken. And you take its curl, you find, in fact, that there's a pattern. It's not a random combination of these 2. It's, in fact, a curl eigenstate. It's an eigenstate of the curl operator, which is, in fact, a beautiful set of functions that I wish I'd been taught about when I was an undergraduate. But anytime you have a curl operator involved, you break things down into curl eigenstates. It's much easier. But anyway, so you notice this, what you do with it? Well, the sort of argument which I want to propose is that, in fact, if it's helicity which you're interested in maximizing, then curl eigenstates are very natural objects to try and build your field in terms of. Because this helicity is an expression for A dot curl A, so there's going to be maximum overlap between curl A and A. So if you're trying to build up your field, you do it in terms of curl eigenstates. The chances are you're going to be maximizing things. So these building blocks are important from a sort of global point of view. Well, what about they're important for helicity. Helicity is about knottedness. Let's go and have a look at one of these single frequency components and look at the field line structure of them. So what I'm going to take is just T plus ITM, and I'm going to take a particular point in space and draw a field line at time 0. And if you pick, you have to pick the point a little bit carefully, but generically you get something like this. This is a curve that winds some number of times around one circumference of a torus and some number of times around the other, which is in fact part of a family of knots. And you can start doing this from all sorts of points in this single frequency component, and you find that in fact these single frequency building blocks contain all possible torus knots. So in this single frequency component there is really a lot of topological structure. And the thing which locks it into phase, the solution which we've looked at is a 1-1 solution, is in fact the energy spectrum. So it's an interesting connection in the linear theory between the energy spectrum and the topological structure of the field lines, which we're still sort of trying to unravel a little bit. Okay. But now you can say, okay, these things seem to be important. I have some idea of what this topological Lego is like. I have these building blocks which have all this structure in them. What are the rules? Or at least what's one of the natural rules? Well, we were interested in states which had conserved helicity, so let's compute the helicity for an arbitrary decomposition in terms of these eigenstates. And if you do that, you get a relatively simple expression, and the only thing which to notice over here is that there's two terms, one with a time dependence and one without. And of course what we want is time independence, a non-zero value. You can kill this term by simply taking only values of m and not the corresponding minus m. So that's your design rule. If you do that, you're guaranteed conserved helicity. And then you take a certain number of plus eigenstates or minus eigenstates. But if you add both, then you start to decrease the helicity. But you could have a superposition of plus and minus, and the helicity would still be conserved, just reduced. Okay? So that's a design consideration. So let's do the simplest thing. Let's do the sort of most naive thing. Let's take the same energy spectrum. The role of this energy spectrum is still not completely clear. And let's just change the value of L and M. Let's put 2, 2 in there, for example, and construct a field. And if you do that, you get something that looks a little bit like this. Okay? This is the sort of looks like a complicated tangle, and it is, but if you look carefully, you can find embedded in this tangle, towards the core of this tangle, some special lines, which in fact are sort of, I want to say, are analogous to this infinitely long line and this circle. And these lines evolve smoothly and look something like this at time 0, but if you look at them carefully, this is just put into a knot plot to see the structure, you see have the structure of trefoil knots. So this is one sort of little first step into designing. But of course, if you look at this expression long enough and you try to really think about how the 1-1 case worked, you realize that there's another thing you can do. And this one's kind of nice. You can look at this and you can say, well, this is a plus state, but if I add it to a minus state, helicity is still conserved. And I can add them in such a way that I get a ratio between this term and this term. And this term takes you around this way, and the other term takes you around this way. So if you make that ratio a pair of coprime integers, you can in fact get all possible torus knots with conserved helicity, which sounds great. It's what we wanted. Okay? This is a sketch of what it looks like. But if you then look at the evolution of this, you see something. And the thing you see is that even though the helicity is conserved, and it has this beautiful field line structure to start with, the field line structure, if you look at it in detail geometrically, falls apart completely. And that's in fact because the helicity is an average measure, and so what's going on is it's falling apart in such a way as to conserve the average, but the individual field lines do not have preserved topology. So if you want to preserve their topology, you have to say, well, what's the minimum ingredient for preserving topology? It's like embedding it in a fluid. If the evolution of the field is a smooth deformation, it's a smooth flow, then I could hope that my field line structure would be preserved exactly.
It's not frozen in fluid mechanics language.
It's not frozen, exactly. So if you want to freeze it in fluid mechanics language, you want to try and close this sort of diagram. Okay? And the field has its own evolution, so there's a time derivative addition. But essentially you want to be able to flow along a field line, flow along a velocity field and time, or flow in time and then along the field line, and you want this to close. And that's a condition which you can write in various ways. but essentially is your frozen field condition. And then you can ask, well, what is the frozen field condition for the magnetic field in a free space? And you presumably you want your velocity field to be flux preserving, you want it to be some physical thing like the direction of the pointing vector moving at the speed of light. And what you can show, and this was sort of work which I did a couple of years ago and then realized there are a few corrections which help the setup and the conclusions are the same, but there's a couple of steps in the demonstration that Daniel Peralta Salas pointed out weren't quite right, but we've worked it out, so there'll be a follow-up on this. But the conclusion is the same. The conclusion is that this condition, the frozen field condition, is satisfied if E dot B is 0. And now I mean 0 identically. I don't mean the integral, the average of E dot B is 0. Okay? This gives you a pretty strong design constraint. And this is, in fact, what I think is sort of the key to designing fields whose evolution is as kind of impressive as the first one which I showed you. And so now you have to worry about this. And if you want it to be preserved in time, you have to worry not only about E dot B is 0 times 0, but you also have to worry about E dot B staying 0 at later times. So it's even harder than you might think. So it's a very, very, very strong geometric constraint. And it's sort of illustrating the fact that you want to design a structure in a magnetic field, you need to have all this additional structure, both in the electric field, and you have to fill space in a way with a sort of triplet of fields, if you want. And so what does that? Right? The key ingredient in making this sort of geometric quantity stay the same through evolution is the flow field. We said it's going to be preserved because of the flow field, so the flow field must have some special properties. And the flow field at time 0, which is given by the cross of E and B, is in fact another one of these Hopf vibrations, this time oriented along Z. But the great thing is if you look at the evolution of this flow field in time, unlike E and B, it doesn't deform. It stays completely rigid and moves completely rigid along the Z-axis opposite the direction of energy flow. And this flow field with this topological structure is guaranteeing the preservation of the topology of E and B. Okay? And of course it's going to have a number of remarkable properties to do that, not least the fact that each fluid element actually travels in a straight line, as you'd expect light to do. This is one of the field lines at time 0 transported by this flow field in time. And these properties can sort of be summarized by calling it, in fact, an object which was known, and this was why Robinson and Trautmann were studying this. It's a geodesic shear-free null congruence. Okay? So the null part is E dot B is 0. The geodesic part is each part is sort of moving in a straight line. And the shear-free is telling you about the preservation of the angle between E and B. And so this is really telling you about not just the condition at time 0, but how the solution evolves. And one of the things which we're doing is sort of going back to use this sort of machinery of this language to construct now solutions where nothing breaks apart and the field lines are nice and closed. Okay? But I'll just put all these together. We're coming towards the end of the first part of this talk, so you can see sort of the full structure of this solution. You need a conspiration of E and B perpendicular and a velocity flow field for free space electromagnetism that preserves the geometry of these. And if that is all true, then you can preserve the topology of this structure. And I can just advertise it now. I don't have really time to go into it, but we've very recently succeeded in using some of the formalisms which were designed for constructing null solutions, which is a problem which in principle has no topological consequence, to design some solutions in free space, constructed in a similar way actually, except instead of taking tori and knotting the field lines on these tori, we're now taking these tori and we're knotting the whole torus and constructing the field around that. So we can construct some trefoil knots, and in fact any twist knot which evolves in time.
So what sort of antenna and signal do you actually make to?
So it turns out I think it's in fact not that hard. So I suggested a way of doing this a while ago. Microwaves, you could think about doing it. It's always challenging, but it's Maxwell's equations. So essentially, it's investment in time and infrastructure, but there's a very deterministic sense in which you do research in optics. You sort of know the phenomena is going to be right, and you get it to work. But the sort of insight comes from the fact that if you decompose it into these spherical harmonics, you have a pure angular momentum eigenstate. And so now you can imagine if you start with a plane wave with pure angular momentum and you focus it down as purely as possible, which is essentially 90 degrees, then the state which you get is going to have L is 1 and M is 1. And if you start with a different angular momentum, you can do that. Now the only question is, what about the relative phase of TE plus ITM? Well, then you can show that TE on its own is in fact a famous state. It's a whispering gallery mode. It's what you get if you have a cylinder or a spherical container and you launch a little bit of light along the edge and it finds a way of whispering around. Called whispering galleries because you can do the same thing with sound. You can sit at one end and whisper along to the other end. So it doesn't go anywhere. And the TM does the same thing. It doesn't go anywhere. The only way in which a solution can go anywhere is with the relative phase factor of I. So you're guaranteed that by the fact that you're taking a beam, focusing it down and letting it go. And then all you have to do is the energy spectrum. That's challenging at optical frequencies, but in microwaves with an appropriate spectrum analyzer it should be possible to do. So I think this is actually doable. My motivation, at least I'm refraining for the moment from doing that, just because what I'm really interested in is, okay, light is, it's interesting from a theoretical point of view. It's a linear theory in which you can study nonlinear topological structure. From an experimental point of view, light really comes into its own when you want to transfer topology to matter. So I'm more interested at the moment in what happens if you take one of these, you shine it onto a plasma, or you shine it onto a BC, and can you use that to transfer topological structure? And that will in turn dictate how you would want to do the experiment.
But if I understand you correctly, you start with a plane wave, right?
Yes.
And then you manipulate with it. But this manipulation dimension involves interacting with charges and currents,
Yes.
which are not in the theory
Exactly.
you're using. So I'm quite confused what kind of, how can you do it?
Well, the interaction involves a dielectric. It involves interacting with charges, but in a way which we understand. So what you can do is you can ask, I come in with a plane wave, then I have this lens or a hemispherical piece of metal that focuses down, and I sort of know what the structure of the field is right after that operation. I'm not going to track it through that operation, but there's nothing that forbids the change. And what I know is what the structure is after that operation. And in fact, it's more than knowing what the structure is after operation. I can use angular momentum conservation as a way of knowing what the structure is going to be after the transformation. So in fact, that step involves charges, but you can put it into a black box which is well characterized and well understood. And then you can look at what the structure of the field is on the other side. But anyway, okay. So far we'll just consider this as a theoretical sort of, I wouldn't say curiosity, but a context in which to study these structures. But what I want to do now is kind of shift. And in fact, probably most of what I'm going to be doing is showing you movies. I want to shift to the topic of vortices in fluids. We're going to go back to this sort of Kelvin hypothesis, because it turns out that even though this idea has been around for a long, long time, to the best of my knowledge, nobody has ever succeeded in creating an experiment linked or knotted or any sort of vortex structure with non-trivial topology, at least certainly not in a controlled way.
I would suggest as we're doing fluids, can we turn the lights off too?
Yes, that might help with some of the videos.
You want the light off?
Yeah, can we darken it down a little bit?
That's good.
It's these ambient ones here.
Yeah. Okay, well, let's see how this goes in a while. The movies are a little bit dark. Okay, so I'm going to shift from classical field theory to fluid mechanics. And of course, the motivation is not just this, not the field motivation which I started with at the beginning. There's also motivation that comes from within fluid mechanics. And this comes partially from understanding complex and turbulence flow. And you can ask the question of whether knotted vortices or vortex structures in turbulent flows are supposed to be there and being conjectured to play an important role in transport of energy and in the evolution of turbulent flows. You sort of picture this turbulent flow as a complicated tangle of vortex structures that are interacting with each other and reconnecting. And you sort of want to see if this topological measure can give you an additional interpretation of the flow. So it's a sort of complicated set of questions, in fact, a rather deep set of questions in some contexts, and a long history to the problem and very little experiment. So I was in fact a little worried about venturing on this. But just as a way to sort of break the mood and also show you something which actually did play a role in my thinking of this problem. Here's a vortex loop made by a dolphin. when you sort of look at this, and you look at how stable it is and how you can manipulate it and how big you can make it, at least my instinct was, yeah, we can probably do this. At least we can try. So in Dustin, my postdoc's representation, way of explaining the problem, we're going to take these things. He's a master of Photoshop, and we're going to tie them into knots and links. Okay. So where do we start? We want to tie these things into knots. First of all, what knot do we start with? What's known? What had been done before? Well, quite a bit had been done before, and that sort of drew our attention to the simplest possible knot, the trefoil knot. And in particular, there's been a lot of sort of theoretical effort in trying to model the dynamics and evolution of such a structure. And in particular, a piece of work by Shigeo Kida, who showed that if you make a trefoil knot with exactly the right shape, and you use an approximation in which the evolution laws for the vortex are local, so the vortex lines move in the flow field generated by the rest of the vortex, and if the vortex is very, very thin, then only your neighbors matter. And so you can come up with a rule for the evolution of the vortex, which is that the vortex moves in a direction which is sort of perpendicular to the binormal. You take the vortex and you fit a circle at every point, and it moves like a ring would move in the direction of that ring that you've focused. Then you can cook up a shape. This is a highly non-trivial problem. You can cook up a shape such that this evolution conspires to preserve the overall structure of the knot. So you can make a particular shape of a trefoil such that with applying this rule to all the points which move along, it just rotates and translates, like I showed you over there, and its structure is perfectly preserved. Okay. Now this is, of course, a very strong approximation, and there's been all sorts of questions asked about its stability, but it's, as far as I know, the only starting point, the only serious starting point we have. So that's what we tried to do. So now comes the question, how do you do this? And well, there's a sort of naive things that you could write down. You could imagine, very, very ambitiously saying, well, these things are supposed to be in turbulence, let's make turbulence, and let's put a knot filter on there and either find them in there or pull them out. That's rather probably not the most productive approach. You could imagine colliding them. And it turns out, in fact, a lot of people have thought about this. You could imagine taking a pair of rings or taking a ring and sort of making it collide with itself or colliding them with each other. Or you could imagine perhaps making them upon emission. You could make some sort of nozzle, some sort of little attachment that you could put on a cigar or something and have smoke rings coming off. But we started with collision because it seemed like a reasonable one. In fact, there was a suggestion by Renzo Ricca from not so long ago who said, well, if you take two vortices, so this is now a vortex propagating into the board, and you perturb them a little bit, so that the first one is this shape and the second one has that shape, then if you do it just right, they're going to approach each other like so, and there's going to be 3 reconnections. And these 3 reconnections are going to leave behind something like this. So it seemed like a reasonable thing to try. So this was a sort of before my labs were built. We sort of set up in a closet, we got a fish tank, and we made the simplest possible thing that you can do, which is a setup where you have a box with a hole. Okay? And the only sort of, say, difference from what you've seen before, or call it innovation, what you want, is we put bubbles in there. Okay? So we just put a fine mist of bubbles on one side, and then we just push a slug of fluid through the hole, just like we did before. If this is where the lights could go down, if that's a possibility.
Oh, good.
It's these up here that are the most
Yeah.
spots.
Okay.
I've heard things magically happening. Ah, there we go.
Any more light? Can we turn out this one, for example? No, maybe not. Good.
Aha, there we go. Okay, thank you. So here we go. This is the same thing you saw before, done with smoke, but now we're doing it with bubbles. What you can see is that you can, well, we knew this, you can make a pretty good vortex ring. The other difference is that this is in water. And the bubbles, they sort of migrate to the core right? The core of the vortex, the fluid is spinning around it like this. The bubbles are lighter than the fluid, so they feel a buoyancy attraction to the core. And they allow you to visualize the core with much higher resolution than if you used some co-flowing traces like smoke. So now we can sort of look at these things and really look at their core structure. So the first thing we wanted to do was make shapes. Okay? And people have tried this before with smoke, but this is our version in water. And all I changed was the hole. I just made the hole have a threefold perturbation. And what you see is that you can very reproducibly and very sort of controllably make vortices with non-trivial geometric evolution. And the evolution, in fact, though it's not quantitatively that of local induction, is in fact qualitatively the same. What's going on here looks like an oscillation, right? But it's in fact a three-dimensional motion with the more curved parts kind of going ahead and the less curved parts coming out and back. And there was a beautiful paper where they worked out some of the dynamics of this sort of structure and did some experiments even with smoke. You can sort of look at this from the side and you can see this three-dimensional evolution. So this was one of the ingredients. The other one is you want to be able to do multiple ones. So here I'm going to show you two rings. And what you can see is that they indeed interact in each other's flow field. And there was also a beautiful experiment of this kind that had been done years ago with ink in water. Okay. In this case, we can perhaps, I'll come back to it later, we can perhaps capture some of the dynamics with more precision. But it sort of shows that if you get things right, this is where you have to start really worrying about your parameters and the steadiness of the flow in the tank to get this sort of thing to work, but you can. So we have two, we have shapes, and the last thing which we need is reconnections. So here's two next to each other to show this. And this sort of, initially I looked at this and I was optimistic, and then I did a bunch of experiments with Dustin, and we decided to look at this and be very pessimistic. You see, when these things join over here, there's this sort of big perturbation that goes around the surface. So we tried all sorts of things, all sorts of shapes. I mean, I'm just showing you a few. We did one and the other. And what always happens is that this sort of reconnection sends this perturbation around, and that always kind of spoils the party. And it never seems to work. And I think this is probably one of the reasons why people who tried this way weren't quite succeeding.
Is that perturbation, I mean, there's a sort of an effective speed of sound or something?
Oh, yes, it's even more beautiful than that. It's a soliton. And you can, in fact, model these things as a nonlinear Schrödinger equation with solitonic excitations. You can see helicity in them. I'll come back to that.
Does it help to use glycerin?
Glycerin makes it worse.
Worse.
Yes, glycerin makes it much worse. What it helps is to, well, there's all sorts of flammable liquids that we're considering at the moment. But water is pretty good. You have to go to explosive stuff before you get better.
Is helicity conserved in your reconnection events?
Huh?
Is helicity conserved in your reconnection events?
The key question of of this part of the
Zero.
talk. I'm going to come back to that.
Zero throughout,
In this case, it's zero throughout.
Very symmetric.
Exactly.
so it's conserved.
Okay, so collisions. I'm not saying it's impossible, but it's challenging, and I think we gradually got to understand why it was challenging. And on one level, this was very disappointing. On the other level, it gives you a little bit of comfort in thinking, okay, maybe there's a reason why these things are difficult to make, and maybe we can make some progress. So back to the other approach. Let's make this fitting that we can put on a knot, which traces a knot, and let's produce a knot that way. So this is attempt number 8. Okay. We tried all sorts of things, closing these holes, not closing the holes. What you're looking at is a piece of plastic. The edge, there's a little lip over here, which traces a trefoil knot in the shape of the LIA solution of Kida. And otherwise, it's made to look as much as possible like an orifice. So we have these sort of vertical lines over here that come up to the lip. The same thing happens over there. And if you put this is now attempt number 9, okay, in the tank. You watch with great trepidation, and it's a horrible mess. But this is an interesting mess. This is a mess you can think about. And so I'm going to play it a few times, and we're going to look at it. And what I want you to notice is that, in fact, in many cases, in many senses, it works. Right? If you look at these lips on the outside, you get a nice curved vortex line which follows the shape that you want. That works just fine. The place where things seem to go wrong are these places over here, these regions over here. And the key to what's going wrong is to look at this point over here, which is not supposed to produce a vortex, but we have little extra bubbles there, and you can see that it does produce a vortex. So unfortunately, what you really have here is 4 holes pointed at each other, and you're going to get all the problems which led us away from that approach originally. So it doesn't work. But it tells you something. It tells you that you've got to solve this problem. If it's a knot you want to make, you're always going to have this situation where you have an open and an open part. And you need to create an object which breaks that symmetry. Because it works when the symmetry is broken, closed open, and it fails when it's open open. And this is a sort of key ingredient. The object which does that is in fact very familiar. It's a wing. You can think of flow over a wing as a superposition of a circular flow around the wing, which is ultimately what gives you your lift, and a linear flow. But this is what took me here. This is probably what took most of you here. This is lift. This is what keeps an airplane in the air. And this is a steady state picture. This is something that you get whilst you're flying. But when you're on the runway, you don't have any circulation. You don't have any lift. So somehow, when you go from being on the runway to flying, you generate this circulation. And so you might have to do something to balance it. And the way in which you do that is by emitting a starting vortex. Okay? This is an acceleration-based phenomena. You accelerate the wing, and it creates a starting vortex. And it's in fact, in some sense, a very kind of hopeful picture of how an airplane flies. It creates one of these when it takes off, and it leaves it behind on the runway. And then those wingtip vortices, which you see, which are finite edge effects, have nothing to do with this vortex, trail off the end and go all the way back to where it took off from. And that's how it closes the vortex loop. So if we take a wing, we accelerate it. Let's take a wing, and let's make it into a circle. And so what I'm showing you over here is a ribbon. It has the cross-section of a wing with the right angle of attack. And of course you have to make these things, which is takes a little bit of work, but you can sort of start with an equation for the trailing edge that you want, and you can build an aerofoil around it, and you can come up with a triangulation like this. And then we can put it into a wonderful piece of equipment, a 3-dimensional printer. And I'm showing you here a time lapse of this object being printed. And this takes about 8 hours, so I accelerated a little bit. And now we can put it in a tank and accelerate it. And although starting vortexes have been studied for a long, long time, I'm not aware of them being used for engineering vortex loops. But there you go. So we weren't sure it was going to work, but hopefully this convinced you this approach works. Yes, we'll come back to that. Okay, but if you're naive, you can say, what happens if I do that? And so this is in fact not going to be a failure. And this was the first experiment in which we saw what convinced us was a knotted vortex loop. I'll play that again. We take this object, we dust it with bubbles, we accelerate it, and it leaves behind the vortex.
Passes through the vortex loop generated by the one below it. Doesn't cut it.
Okay. So that's the part which I'm not going to go into great detail about, which we're studying very much at the moment. It turns out that you can't just take the wing and tie them to a knot. You have to worry about the crossings, and you have to make some modifications at the crossings. But there's a parameter space, which we found experimentally, by which if you reduce the angle of attack at the cutting points, it doesn't disrupt the vortex which is cutting too much. And then you can get away with it, and you can get the vortex which was cut to reconnect. Okay. So this is a sort of modern version of it. That was the first one we ever did. This is a slightly higher accelerations. And I could spend a lot of time showing you this and trying to convince you that this crossing is over that one and that crossing is over that one. But knots are 3-dimensional objects. You really want to see them in 3 dimensions. In fact, they don't exist in other dimensions. So we developed some 3-dimensional imaging. So Dustin built this essentially contraption which produces a laser sheet, and it scans back and forth. Okay? And I'm showing it over here at very reduced speed. You just take a cylindrical lens, you produce this laser sheet, and you scan it back and forth. But of course, everything I showed you is relatively fast. We use high-speed cameras, so we want to do this very quickly. Okay? So there's a few tricks in doing that, but we can do it so that we can get 500 volumetric images per second. So we're collecting images at about 100,000 frames per second. And what you can then do is, by knowing the time at which you collected the frame, you know which part which is being illuminated corresponds to which depth, and you can reconstruct the image in 3 dimensions. So this over here is going back to that threefold distorted loop, but just to show you that now we can sort of image it in 3 dimensions, really see the structure of the flow, and rotate it at will. And so now if we do that for this case, hopefully I can convince you that it is indeed a knot.
You should have stereo glasses though also.
Yes, I can make this stereo if anybody has stereo glasses. Just tell me, I'll press a button.
So, what we are seeing is ink or bubble?
Bubbles.
Bubble.
Yes. The bubbles are attracted to the core. Now, is this a fluke? Is this the only shape that made it, and the only time that we've seen it ever, or anything like that? So let me try and convince you it's not. Here's a whole series of them. Okay, we've made them to different scales, and we accelerated them to different speeds. We took a lot of videos like this, and we took 3D data sets, and then we rescaled them. So this is now results from a lot of different experiments. Okay? And I'm showing you over here just 4 different size objects. In fact, 3 of them are different sizes, and 1 of them is a different speed. And I've taken the snapshot at the same time, rescaled by this scaling that comes from the speed and the size. And what I can then do is I can take these and I can stretch them spatially also to show you that they collapse. So it really is sort of behaving in the way that we expect, and it's very deterministic. What I've showed you so far is just the trefoil knot. How general is this technique? Can we extend it? Is it just lucky that it works for the trefoil knot? Well, we can, and here's the other elemental configuration. 2 vortex rings. So we're sort of working on understanding some of the details of the production quantitatively, and to allow us to do arbitrary configurations, but I think it's a promising approach. And all those considerations have to do with the crossings, of course. So we made one. What does it do? There's all these questions that people might have. So the first thing which we expected is to see whether it followed these dynamics, which would, you'd expect from LIA. Does it rotate, for example, as it goes forward? And here's the sort of first stages in the evolution. And you can see, in fact, it rotates the way that you would expect it and the way that you would expect it.
So the fluid is not rotating.
The fluid is not rotating. But what happens if you then let it go is a big difference from what you expected from this linear induction. What you see that instead of preserving its shape, it deforms considerably, okay, and it evolves towards a shape in which the strands get closer and closer together, as you see over there. Okay. In fact, what happens is this object appears to untie itself. And I say appears slightly
So
provocatively.
it reconnects.
Yes, it reconnects. So in fact, you get the development of these 2 ring-like structures, a perturbed threefold big one at the back, and a faster, smaller one at the front. And then, if you look from the side, there are 3 points at which you get reconnections, and the 2 rings come off.
So Renzo was right, you said the arrow of time backwards.
I guess that's one way to put it. But let me zoom in, because this is a key step, and this is one of the kind of key questions. Can you use this sort of system to understand this process of reconnection?
Wow.
And so what I did here was just zoom in to give you an idea of the fact that we can...
My comment was actually half serious too. It seems like there's a stable and unstable direction.
Mhm.
But Renzo identified a very unlikely unstable
Direction.
whereas it's really
There is some morphogeometry.
But the key question which was asked earlier is this really an arrow? So what you've seen is the core of the vortex, and you've seen the core of the vortex break up into 2. But does that mean that you've lost a knot? Apparently you might think so. But in fact, there's another way in which the vortices can preserve the knottedness, which is by twisting internally. The vortex lines which go along the vortex can in fact twist along the vortex core. So if you imagine taking a vortex core with no twist like this, and you imagine that these are parts of this which are coming together to reconnect, you take one of these, and I'm just going to twist it. 1, 2, and 3 times. So now we have twistedness inside a loop which resulted from this reconnection, but in fact, twistedness in the core is a form of knottedness. If I can straighten this out, you can see it's I'm doing torsion, so it's a little hard. But you can see this is a trefoil knot, okay, depending on the number of twists. And this is the future, really. This is where we're going now to try and understand this sort of configuration. Huh?
You've got a track of framing or a fraction.
Well,
It's a fraction.
or you can go back to realizing that the helicity expression A dot B in this context is U dot omega. So if you have transport along the vortex core, which is something you can image, like we do image, then that gives you a handle on tracking the helicity. The other one is you can consider bounding surfaces which bound the knot, and you can look at topological structure of the flow on these surfaces as a way of inferring. Just to put it all together, as we're getting close to the end, here's the whole evolution of the trefoil knot, and here's a sort of cartoon representation, if you want to take something home from this, with some suggestive notion of twist being preserved in there. And, this is the other mechanism for twist. So this I'm not quite sure what it. Oh, it's just a repetition. Here we go. So the last kind of few minutes, I just want to show you a few of the steps which we're taking in making all this more quantitative and looking at the energy and the helicity flow. The helicity flow will be for next time. This time I'm just going to tell you a little bit about the energy flow. So the first thing you have to do is you have to find the loops if you want to do quantitative things. So we do some sort of fast matching algorithms, and that allows us to find the loop in 3 dimensions with software. So the first thing we can look at is, for example, what happens to the length of the loop as a function of time. And here I'm just showing you, this is what that threefold perturb one does. A ring would just stay perfectly constant. This is over actually a long time scale. If you sort of zoom into this region over here, you can look at what happens to the length of the link and the knot. And what you see immediately is that they sort of grow much, much longer. Vortex stretching is really driving what is going on. And so if vortex stretching is driving what is going on, can we use that ingredient to understand what's happening? And it turns out that you can if you just think of the energy. Okay? So the energy in one of these flows is the kinetic energy of the fluid, which is surrounding the vortex. You can figure it out by saying, well, how much energy do I have to put in to generate a certain amount of circulation? But that's exactly the same question as asking, how much energy do I have to pump in to a current carrying wire in order to generate the magnetic field? Because the magnetic field is the analog of the velocity field, if you just translate the same equations across. And so by just finding the shape, so the circulation is an analog of the current going through the loop. The density comes into it, of course, because it's energy. This is the kinetic energy for the vortex. And the other object which comes into this is the analog of the inductance. And it depends purely on the geometry of the shape. And so what we can do now is we can put that inductance in, assume the circulation is constant, which is an assumption, but it's our first steps in this. And you can ask what happens to the then energy of the vortices. And what I'm showing you over here is this is the length, it's the one we looked at before, but the energy turns out not to have any dramatic changes. The energy which I'm showing over here, which is the energy for a constant core, assuming there's no change in the size of the core, is roughly flat in all 3 cases. Okay. In fact, the energy sort of decreases viscously if you include the fact that there's viscous diffusion in the core. But separating those components out is a little subtle, so I'm just offering them as alternatives over here.
What are the 2 colors representing
the 2 colors? So this is the just the inductance that comes from the shape.
So the energy is the orange one, or the...
Well, the energy, you could take it to be this, if you assume that the core is not viscously diffusing. But if you put viscous diffusion as square root of 4t, then this is the energy. And what you see is that, in fact, in this case, it decreases quite a bit, but that's because it's a long time scale. Over here, it brings it down gently, and over here, it does the same. In fact, in some cases, we can track it through the reconnection. And when we track the energy through the reconnection, based on this assumption of constant circulation, which I'm not going to try to justify at the moment, we see that the energy is approximately conserved. But the interesting thing is, if you think about the problem now as an inductor, how do you undo inductance? You undo inductance by taking a wire with current going this way and current going this way, and you put them opposite each other. And so if your wire is lengthening, The only thing you can do with your shape in order to keep the energy constant is to try to anti-align your wire. And if you anti-align your wire, you start orbiting, you start twisting, and eventually you reconnect. It's a sort of first step in understanding.
Your energy is a rotating
Huh?
Your energy is not Galilean invariant. So
Yes.
So that E12 is the rotation part?
Yes,
or-
exactly. Exactly. We're not considering the Galilean.
And I think the connection always occurs anti-parallel.
Yes. But this is a slightly stronger statement than saying if you lengthen, then you have to reconnect.
This is a quantitative version of the anti-parallel.
Yeah. It's not a mechanics of it. It's saying if you do lengthen, energy forces you to reconnect because it comes in as the geometry of the loop. So that's sort of steps towards the future. To conclude this part of the talk, we've sort of developed a technique for patterning vorticity in 3D and imaging it, and it's allowed us to make knots. And I should finish by thanking my collaborators. This is Hridesh Kedia, student, theorist, working on null solutions of Maxwell's equations, the part which I didn't have time to really go into, but he has some beautiful generalizations. This is Martin Schiele, PhD student, and Dustin Kleckner, who are responsible for a lot of the vortex work. Thank you.
Well, thank you. It was a brilliant seminar. Both parts. Brilliant two seminars. Yoshi.
So bubble visualization shows looks, the vortex is very thin.
Yes.
But I wonder exactly, vorticity is really concentrated as thin as bubble shows or bubble implies.
That's a good question. You're asking what the size of the core is.
Yeah.
So if you, what I can say is, that's the sort of thing we're trying to measure at the moment. It's a little tricky. If you assume that you start with 0 thickness core, then, and you take viscous diffusion as giving you the size of the core, then the size of the core would be below what I've shown you. So it is really concentrated. But if the process gives rise to thinner or fatter cores, as far as we can tell from scaling and so on and so forth, it doesn't seem to be the case. But a real image of that is challenging. It's one of the things we're trying to do because it feeds into this helicity measurement. But it's a subtle measurement.
So in your reconnection event, you said you get anti-parallel alignment, you get some twisting,
Yes.
and then that's what produces, even though the cores become unknotted, that's what produces sort of torus knots along those unknotted cores.
Quite possibly, this is the conjecture, and we hope to have an answer soon.
So just sort of following up on that, so during the talk I asked, not mathematically, but physically, how can you mark it? You mentioned inks were used. I'm just
Yes.
wondering, is there a way to mark the framing somehow experimentally?
Yes, there is. So you can use different colored inks, you can color different points of the flow and
So you might be
track
able to
them.
see that rational framing somehow if you could get a couple of...
Yes, it shows up in a relative phase though, which is a tricky thing to
There's
measure.
actually one that's a different one, which is the wing approach to synthesizing the
Yes.
coordinates. How about like a magnetoseptic inclusion of the fluid and then using...
Oh, we're playing with that too.
Yeah, so just, but
Yes. I mean, look, this whole thing started with sort of, we were thinking about, well, we were pretty depressed because it wasn't working. And we were thinking of all sorts of crazy ways of doing this. And one of the ways which we thought of was, well, what if we do the simplest thing you can imagine? We take a wire, we tie it into a knot, and we spin it on itself really, really, really fast. So essentially we force a vortex there, and then we come and we whack it. And hopefully we can get it off, right? If we're quick enough, maybe, I don't know. But it turns out that's exactly what we're doing. If you think about that and you ask how fast is the flow going close to the core, it's really, really fast. And if you wanted to do this mechanically, it would be really, really hard. You'd need a wire, a horrendous motor, and this doesn't work. But that's exactly what a wing does. It has this circulation that goes around it, and what you're doing is you're whacking it off by accelerating it. So in fact, it's much the same technique. And if you try to do the same with a magneto-responsive fluid, which we're doing, by the way, you can't just put bubbles in these things. You can put ferrofluid, for example, and you can pull on them and do all sorts of things. But that's the future.
So I would like to ask if you think that there could be a possibility of imprinting the this kind of patterns into the biological soft matter, which say aggregates in the fluid. So like you prepare one of these complicated topological flows and you have like aggregating colloids or proteins aggregated into fibers. Would you say that there could be a possibility of getting non-trivial topological structures out of it?
I think so. There's a lot of degrees of freedom you can play with. One is the buoyancy, which will attract things in and out, but the other one is the strong shear, which comes from the flow, and you can use this to pull string-like objects in and have them align. And there's no scale in it.
So that this kind of thing can imprint certain chiralities, handedness of the biological polymers?
It's a good question. It's a little bit speculative, but you are imprinting a certain handedness on the flow at a large scale, which then goes to a lower and lower scale. But I think that handedness should somehow carry across. And so as you go smaller and smaller, maybe it could help. It's a little bit of a speculation.
Yes.
Since this is buoyancy driven, then maybe you can improve focusing by introducing by designing temperature field. Like if you have temperature gradient so that it's colder in front, that maybe just wouldn't go to the sides. Is it?
Yes.
I'm just a theorist.
No, that's a good. Temperature is one of the temperature effects. Not only sort of also phoretic effects, but also the viscosity. So you can also try to make things go a little bit faster by changing the viscosity around the edges and use that to focus. The other thing you can do is you can put these things in stretching flows, which gives you a big leap in Reynolds number. But we couldn't really do any of it without making the thing in the first place.
Along the same lines, maybe one can get such things in porous media by designing the size of grains.
Yes.
And having two cylinders meeting.
And getting a topological flow in the porous medium.
I was curious about the first part of the seminar. You showed fields on a toroid, but you showed them using Cartesian coordinates and sometimes spherical coordinates. Why not use toroidal coordinates?
You can use toroidal coordinates to represent it, but then if you try to solve Maxwell's equations, this is why it took a while to figure out the spherical harmonics were the right thing. You look at that and you think toroidal. But in fact, you have one toroidal, you have a different toroidal set, and you have a third toroidal set for the pointing field. And so at time 0, you can describe one of these structures simply in the toroidal coordinate system. But then your other field is rotated by 90 degrees, the other one is rotated by 90 degrees, and when they evolve, they deform on top of that. So actually, when you try to solve it, it's not so easy in toroidal coordinates. It's the first thing I tried.
You mentioned at one point the Beltrami fields, curl F equals lambda F. That worried me a little because there aren't any localized Beltrami fields of finite energy. And your total field has finite energy, obviously. So, so how do you get around that?
Well, that's what the energy spectrum does. The energy spectrum gets your cancellations to be stronger in the outer regions and constructive. It's interference.
It is,
but it's topological interference.
Yes, right.
It's a linear combination with different frequencies.
Exactly.
That's it. Yes.
Otherwise, it would fill space. But plane waves aren't physical either.
Yes.
It's a tricky interference problem.
Well, I think we should bring this discussion to an end, but I'd just like to say I think this is fantastic. It's a real breakthrough experimentally, certainly in the second part, to produce these vortices in this way. I've never seen anything like it before. I think it's a terrific breakthrough. So congratulations.